Good morning, everyone, and welcome back to the fourth day of this workshop. So this morning we're going to conclude the calibration lectures, and Ben again is going to present some self-calibration and also a recap of the calibration for us today. Over to you, Ben.
Thank you so much, Ruby, and welcome back, everybody. So I think this is the penultimate lecture on the topic of imaging and calibration, which is really intertwined. Josh is going to show you a bit of H1 analysis later on. You will see that the interferometric imaging in the models that we've constructed during that is going to be vitally important for us to be able to subtract the foreground AGN so that we can image the remaining spectral lines in the data. But I'm not going to steal Josh's thunder, a bit more about that later on. So we're going to move on to the topic of self-calibration. And as I said, this is really intertwined with imaging. You can't really do self-calibration well, easily without imaging, at least. So you need some initial guess for your sky model, right? And you get that through most easily through a process of deconvolution inside imaging. Well, let's take a look what I mean by self-calibration. Well, in self-calibration, we are going to calibrate the target itself, right? We have at this point already done our transfer calibration, or what we also call the 1GC or first generation calibration, by interpolating bandpass solutions, so frequency response solutions from our primary calibrator, and time variable, primarily phase solutions from our secondary calibrator, which is hopefully closer to the target field. As I said before, these really bright quasars that we use for our bandpass calibrators, they are very few and far between, at least those with ideal properties. So there's only really two that we recommend for Meerkat, that is far enough south, are compact enough, and are bright enough to be able to be used for bandpass solutions, because you solve per channel in that case. So they're really far and few between. So what we need is another little calibrator closer by that we can track the temporal variations of primarily the ionosphere, and if you don't have a temperature stabilized system such as Meerkat, also the amplitude variations in your electronics over time. Now, I've already shown you an example yesterday, just so that you have an example on hand. But in self-calibration, we make a model of the target, and we calibrate the visibilities to the target, to that model of the target. We then go and image again, and we repeat the process. Now, why do we do this? Well, there are going to be still phase variations during this period, right? So the phase of the system is not going to stay stable with time. Over here in the bottom right-hand side, I have plotted the phase variation that you get from a typical gain solution over a long track on a calibrator as a function of time. So here on the x-axis is the time from start in minutes, so the arbitrary start time, let's say start time of 0. Then I plot the interquartile spread of the phase variation of the initial solution. So I solve for a solution here. So I phase up the system as in our slang terminology. So you'll see that there are delay cals and phase up operations when the telescope is built and prior to your target observation. That essentially phases up the system, right? So I'm doing exactly the same here. I'm solving for solutions here at point 0. Then I apply it and I solve for solutions as we move along. And the spread of those solutions compared to the first solutions is what is plotted on the y-axis. I plot the interquartile spread just to get rid of any outliers. Now, you'll see clearly that on the short spacing, the phase is quite stable over time, but as soon as you include the longer spacings, so let's say up to 4,000 meters from the very center of the array, so up to the longest spacings really in the array, then you'll see phase variations that are in this gray line, for instance, that is substantially more, right? And this is, as I said, this is phase variation. It's not amplitude variation, it's phase variation. So that there is definitely an ionospheric component coming into play, because that will be the primary driver of phase in the system, and probably also some systematic residual issues. These, we have noticed that there are residual cable delays that change on the order of tens of picoseconds, tens to hundreds of picoseconds. So that is still substantial. If you're trying to do really high dynamic range imaging on a field that has bright AGNs in it, and you want to go down to see your star formation population, for instance, it is still a big problem, just because those bright AGNs are going to highlight the any residual errors that you have in your data. So we do have to keep track of these phase variations within the target scan. Typically, we will separate our target scans from our gain scans in the range of about 20 to 30 minutes. So within that, we want to be able to calibrate not only just the constant phase, but also any changes in the cable delay. So, but that we only do once we build up a reasonably good model of the target field. Now, all of the strategies on how to select gain calibrators, etc., Ruby has covered yesterday, and I think she's going to repeat it during lunch, because I think there were a few technical glitches there. It's quite important information for those of you that are planning to propose for scientific observation on the telescope. There's a wealth of information on the user portal on how to select these things, how the cadences, how do you model direct potential direction dependent problems from bright sources by looking at catalogs of the sky from sets, let's say the NVSS catalogs or SUMS. All of that is covered inside the user documentation. So please do go look at that, and I think Ruby will show that again. Now, let's get on to how we do self-calibration. So what we do is we input transfer calibrated visibilities, so 1GC calibrated visibilities, and we derive an initial image of that, and we derive a model. Now, especially during the first few rounds of this process, we do have to constrain the model really well, because we will have substantial calibration artifacts, primarily from phase at this point. So we don't want to include those artifacts in the model, because then our process is mute. We're not going to see any difference. We might actually see things worsening. So it is very careful to constrain your model to not include artifacts during this process. Then what I've given you an example of that in the notebook. Feel free to go back and look at that. There's things like a mask that the user can put in. You can have auto masking inside the images. So some images support auto masking. There's all the thresholding, so the SNR cutoffs for your deconvolution process, etc., etc. So all of that is used to constrain the model to the actual flux in the sky. Now, we calibrate the gains using that model that we derived. So as I said yesterday, the imager will Fourier transform the model for us, put it in the model column of the measurement set, or in the case of CASA, you can also keep it in a model list, and it will Fourier transform on the fly during gain calibration. I always put my model in model column just so that I can plot it up and see if there's any issues, if my calibration fails for whatever reason. So, but that's just me. So we have that in the model column. We calibrate our gains towards that new model. Now, that model is not just a point source, it's a complicated field. So, so we should be able to constrain our gains much better, because we're using, we should be using most of the flux in the field, and you should be careful to include as much of the flux as possible. We start off with typically of calibration solutions at long intervals, so that if we do have a model that's slightly incomplete, that we have the facility to wash out some of the components that are missing off axis. So we typically start off with longer intervals. And as our model improves, we work our way back to finer intervals. Then we take those solutions, we apply it to our target field, and we go back and re-image and rederive a next model if necessary. If you're happy with the final quality of your image, if you can do your science, then you stop. There's no need to drive dynamic range if there's no need for it. It really just burns carbon, really, because we're running these operations on large machines, so we can stop whenever we can reach our science goals. So let's take a look at probably one of the worst case worst cases for this type of self-calibration process using traditional clean. Here I've shown a portion of the galactic field on the left that has been transfer calibrated, but it hasn't been self-calibrated at this point. So it's only gone through 1GC. Now you'll see that there are strong radial artifacts stemming primarily from the long baselines. Remember that yesterday I gave you a small measurement set containing only the core antennas and some of the intermediate spacings, just so that things can be kept small, but they don't contain the long spacings. Now, the long spacings, as I've shown in that accumulative plot, is subject to the worst of the errors. So what those gain phases and gain amplitudes and things actually does is it decouples the system response from the ideal system response. So the system response isn't quite that theoretical PSF. It's slightly different. And that decorrelates our deconvolution process from the response that the system actually has due to the residual calibration errors in the data. So what you'll see is these spike-like structures that looks like the PSF of Meerkat. So if you include the long spacings at slightly lower robust settings, so closer to uniform, then you will see that there are side lobes, and on really bright sources, as I said, those side lobes that are decoupled from the theoretical response is going to show up very strongly. So here we have these stellar nurseries, for instance, these patches of H2 emission, which is contained in, which is ionized by dusty patches where new stars are born. So those are really bright patches because those stars are really energetic and they ionize really a lot of the hydrogen around them. Then we also have supernova shells here, so it kind of shows the life and birth of also the birth and the death of stars in our galaxy. But this image is not quite ready for publication yet. So what we want to do is run this through at least phase calibration. What we have at our disposal is, well, single scale clean and multi-scale clean. I've used a combination of both here to get the bright fluffy stuff out, and then the remaining diffuse emission through multi-scale components. And if you image it like that, you mask it properly, you calibrate the phases, you repeat many cycles, you calibrate the changes in the cable delays, and so forth and so on. Then finally you end up with an image like I show here on the right-hand side. This is at a slightly different robust setting, but very similar to the robust setting of the first one. And you'll see that everything is much improved. There are still a bit of negative bolts around these sources. As I said, we are missing the mean amplitude of the sky because we don't include the autocorrelations when we image or calibrate. And because of that, our interferometer is going to be sensitive to just the offsets of the mean. So for the really large scale structure in sky, you will have a bit of negative bolts around them in the end. But as I said, a lot of those artifacts, these stripes and the negative bolts and things around these sources are actually phase errors to start off with, and then what you end off with is just primarily zero spacing issues, really. So those missing zero spacings are a problem if you're imaging really, really diffuse stuff. So this is why things like H1 intensity mapping inside the plane of our galaxy is done with single dishes, right? So because we are interested in the really, really fluffy stuff in that case. All right, so that just gives you an example of what is possible even with the limited deconvolution process that we have in clean. Then I get onto the topic of direction-dependent calibration, so what we call third generation calibration. So that direction-independent calibration that I've shown you over here. So this is just gains that are applied to the entire field. I haven't isolated any patch of sky here and applied a specific gain towards that patch. I've applied a electronic gain, so just the time and a coarse frequency dependent gain to the entire field, everything in the field, and it corrected everything. But if you have strong sources that is sitting off axis, especially in an instrument such as the VLA, where the VLA is essentially a Cassegrain system. So it has a primary mirror like Meerkat. It has a secondary mirror like Meerkat, but that secondary mirror is placed in the center of the in the center of the primary mirror, so just above the primary mirror, and it's held up by support struts which interfere with the signal that we're trying to measure. So what you'll see of the VLA is this is in L-band. You have the primary beam response, which is fair enough. This is where your science is going to live. We typically don't do science outside of this, although it is possible to recover fluxes if you have a good model of the primary beam, but we typically do not do that. We just image large portions of the sky so that we can subtract out sources that is interfering with the center of the image contained within the primary lobe. That's just why we image out beyond the primary lobe typically. So we have the primary lobe here of the beam, but then because of those struts, those four interfering struts that is holding up the secondaries, right? Those struts introduce this this varying response in the second and subsequent lobes of the far field response of the VLA antenna. And say we have a source indicated in yellow here sitting dead center in the second lobe here. Now you're going to have the beam introducing time variable amplitude variations or modulations across that source as a function of time because of parallactic angle. The VLA is also on alt-azimuth mounts, so it's subject to parallactic angle. Remember that parallactic angle is just a rotation matrix that takes us from being nominally aligned northeast in our polarization to be slightly misaligned off that nominal east toward our local zenith for any given point in time. That zenith is going to change as a function of time with respect to the celestial sphere, the celestial horizon. So if you're on an alt-azimuth mount, of course. So with that, this primary beam response of the source is going to decouple the total instrument's response from the theoretical PSF that we've calculated just using sampling function. Now, there are many ways of skinning this cat. One way of correcting for this is to apply an average correction inside a small patch of sky through the faceting process. Not only do we use faceting for doing just wide field corrections, so W non-coplanar corrections, we can also use faceting to apply approximately constant grading responses for all the visibilities corresponding to that patch of sky. And in doing that, we can correct for the primary beam response, given that we know the primary beam response well enough and they don't change a lot between antennas. This is not quite true for Meerkat. The primary beam response is quite elevation dependent, and it is quite there are substantial changes, especially in the polarimetric response of the far field between the various different antennas. So applying a single antenna correction doesn't really give you very good polarimetric corrections, at least for Meerkat. So there's a lot of work still ongoing on that, on wide field corrections for leakages off axis. So, but let's have a look here at the 3C147 field, which is a really bright calibrator that is used for the VLA. It has these off-axis sources, so these what I call the troublesome trio. They're sitting in the null and in the first lobe, depending on which frequency you are at in the L band. And because of this, they have this antenna-induced amplitude modulations as a function of time. And you can see that after you've done your 2GC carefully and you've subtracted out the primary component, the primary quasar that is 3C147 itself, then you're left off with these sitting over here somewhere in the first lobe. And you can see these radial artifacts around them, which is not physical. It's residual calibration errors primarily because of this primary beam response. Now, if we apply a correction through faceting, then we get this out, which is substantially improved. And this is just knowing the primary beam. We don't even have to solve for it. Both the Meerkat and the VLA beams have been measured through a process known as holography, where you use one antenna to track a point on the sky, say the position at the primary source, and you use another antenna to track over the region over that source. And by doing that, you get the voltage response of the antenna. So we use that process to get the beams out for Meerkat. Similar things have been done for the VLA, and this is how we got this. It's just a smoothened version of that. So this is already good enough. There's no calibration at this point. It's just being applying what we know. And we can see that the Stokes V component also goes down substantially, so that can be used as a barometer for how good your off-axis calibration is, because as I said, typically our AGN population is not highly polarized, and they're even less so in circular polarization. There are things like stars which do have quite a bit of circular polarization, but they're few and far between. So the predominant driver of flux in centimeter regimes is our AGN population, our radio loud supermassive black holes. All right, and you can see on the left-hand side here, before we apply the beam, there are significant artifacts that is just leaking into Stokes V. After we've applied the beam corrections, they are substantially reduced. Okay, this brings us to DD calibration, though, which is solving for the unknown. We have perhaps the beam, but the antennas may be pointing slightly offset where they should have been pointing, or there are residual ionospheric errors, such as we see for LOFAR, for instance, where we operate in much lower frequency regimes, and the ionosphere electron content in that case, coupled with the magnetic field strength of the Earth, will introduce a rotation in our polarimetry. So it will rotate rotate power between Q and U, and it will also give us delay errors even in the total intensity, so Stokes I. So the sources will be shifting slightly in their position as a function of time, as you observe, and that introduces substantial errors, at least in the low frequency regime. So I'm talking P band and lower. So this brings us then to solving for such terms, which we really don't know at high enough cadence and so forth. There are ionospheric measurements, but they are separated few and far between because they typically derive from our GNSS satellites. and those are spaced few and far between. So the solutions we get from them are typically too coarse to get high dynamic range images out just using those known solutions. So what we do inside the imaging operation is we solve for a direction gain towards a patch of sky. Now, this can be done in many ways. So there are various implementations here. So for instance, in LoFar, you can use the combination of DD-Facet and KillMS, which will split the sky into a bunch of tessels, and it will solve for a solution, again, as I showed here, for a bit of sky. So it takes all the components lying within a small region, it Fourier transforms that to get the model visibilities, and then it solves for a gain for antenna P and antenna Q for all such pairs, for all such directions here, right? So this is the direction, and you get a correction based off that. Here I'm showing also how you can do peeling with this, so how to remove strong sources using cubicle. Although this is possible in CASA, there's so many steps involved in CASA that writing recipes is really hard. And you also have to peel off sources one by one with CASA, which makes the process just too hard to really use in practical everyday use. So what we use is a package called Cubicle to do our peeling. So in this, the Cubicle allows you to construct arbitrarily flexible error vectors. So just as we had before, where we had just data vector minus a model vector modulated by some gains, right? You may recall this is just slightly more complicated than the one I've shown in the lecture yesterday. Here we have, again, gain terms, gain P and gain of Q. So these two antennas, P and Q, for all such antennas. These are direction independent gains. They apply to all of the sky. The sky here is given by both the part of the sky which is not affected by these direction independent errors. So all of the fainter sources off axis across the entire sky. So this is just the Fourier transform of all of those fainter sources as it's given by the imager. So this has already been Fourier transformed. And then in addition to that, we add all the directions that do have these additional gain offsets, both in frequency and time, amplitude and phase, that is giving us errors and problems off axis. So what we could do then is essentially just Fourier transform those patches and solve for them simultaneously with all of the rest. Now, as I said, the visibilities here is derived by Fourier transforming a patch of the model, right? So not all of the model, just a patch which is subject to these errors. I show the process over here. So here I show, let's start at the top left-hand side. This is CASA phase, the first phase self-calibration of CASA. This is the triangulum australis field that I showed you yesterday. It is just at slightly lower brick setting, and it contains all of the data in this case. And this is this was taken with the early science shared risk observations by the observatory. So back in I think it was 2017 or 2018. I can't remember now, but it's no, not definitely 2018. 2019. So it was way back then. But in any case, so I've applied phase calibration, some initial self-calibration, a bit more phase calibration at a bit higher cadence because I've now captured a lot of the model, right? So things improve even further. So this is just direction independent. This gain is solved for using all of the flux in the field, right? And it applies the gain equally to all of the flux in the field. Now I solve for a delay in phase. If you have a really, really bright AGN, this typically gives you a even better result. We always do this now for Meerkat if you use imaging of the long spacings at least. And then you can see there's still issues here. So the source is driving errors. There is some coupling between the direction dependent errors and the direction independent errors. So we solve for the direction-dependent error by practically in DS9 going and drawing a region around that. We're using a region file in DS9. We take that region file coupled with the source model we get from DDFacet, and we plug it into Cubicle, and it will go and solve for that exact rhyme that I just showed you. It will solve for phases applied to the entire sky and for amplitudes and phases that apply only to this little patch and the sources that are contained within this patch. And you can see that there's a substantial improvement from doing this whole process. We find that the solvers in Cubicle typically constrain typically improve over the solutions that you get in CASA, because we have the ability to apply full 2x2 solutions where CASA uses just a linearized form of the rhyme. All right, so all of this is implemented inside the Cubicle package. You can also use, as I said, KLMS on top of this, which applies solutions in the image space, but that splits the sky into tessels in a somewhat automated fashion, so this peeling process through Cubicle is slightly fine-grained, provides slightly more fine-grained control, and we typically use a combination of both this peeling approach and KLMS. At least in the mighty images that you will see coming out of Meerkat, both of those are used in order to drive down the direction-dependent errors. There is a catcher here. So things to watch out for is model incompleteness, because, as I said, we are increasing the degrees of freedom here because there's more gains involved. So if you have an incomplete model, so if you, for instance, have a sky looking like this is really one of the worst possible cases. You have a 3C source actually sitting just off axis in one of in the first null and slightly beyond into the first side lobe. So this is a 3C source. We want to look at a really faint source. So this was the corresponding Meerkat map that was followed up on the first LIGO detection. So we wanted to see something that was really, really faint in the center here. But this source interfered with that, and the side lobes from this, even on axis here, was so substantial that it was much higher than the source that we wanted to detect. So we first had to get rid of this source. Now, we did this through peeling, and if you do it through a traditional way in CASA, where you essentially phase steer your visibilities to the source that you want to subtract, so this bright source off axis, sitting over here, and you neglect the rest of the sky, and you just have make a model for that particular source by masking it, then you're going to get something looking like this, because there's so much diffuse emission in the sky that you're going to be absorbing a lot of that flux, especially on the short spacings, into those direction-dependent solutions, and you're going to end up with these ghost sources, so these ghost patches of negative flux inside the image, and this is not ideal. We can't do our science on this. So if you include the model, as I've shown in this construction of the error equation, so this rhyme, if you include the rest of the sky coupled with the little patches that you want to get rid of, then you end up in a much better situation. And this is shown here in the image on the right-hand side. And this is what we used, and we actually made a detection of that, of a brightening source at the position of the LIGO detection through multiple observations. So it's really important that you're cognizant of the effect of direction-dependent errors. In the Meerkat user documentation, there is actually a section showing you exactly how to simulate for such direction-dependent effects, given a catalog that you can get from, say, the NVSS, and you can apply pointing errors to the Meerkat beam and simulate visibilities and see what kind of effects you can expect in the images that you get out after your observation. So I would say it's always better to plan ahead and to move the source further away, for instance, and therefore diminishing its response in all the frequency channels so that you can do your science. Good planning is always preferred to going through this very tedious process of direction-dependent calibration. So if you can plan ahead, please do that. It will make your life easier and it will pay significant dividends later on. So as I said, this on the left-hand side, we neglected the model, and on the right-hand side, we included all of the flux in the sky when we did the speeding process. I'm going to show you some examples just to give you a feel for what we do in practice. The example that I gave you yesterday, as I said, is not a pipeline. It's just a script showing you some of the steps that is taken in a pipeline. I'm going to show you my pipeline that I wrote a while back. This is executed using our containerized Stamela framework. Now, I'm going to first show you how to put together a basic recipe in Stamela. So just how to pipeline things, different packages together. So the great advantage of using something like Stamela is that you not only have access to CASA, right? CASA is a great tool. It has fantastic components to it that essentially encapsulate the entire reduction process, but there are other scripts out there and other tools that add further value to the reduction process and further diagnostics, for instance, and so forth, automated flagging processes, and so forth. So it is a great advantage if you can tie all of that stuff together in a single script by not having to install 100 different packages, right? That's the last thing you want to do, right? Because each time you rebuild your system, you have to go through that process all over again. So in Stamela, we provide a containerized framework. So all of the tools is already pre-compiled and put in images on Docker Hub and on another Mirror Hub, so that you can just download those images and just execute them. You don't have to compile software. You don't have to install software. You just install a simple Python package that I think the most prominent dependency of Stamela is YAML, right? Because it uses YAML to internally, and I think that's the most dominant dependency. So there's really no dependencies for the package, so it makes the installation process much easier. So if you run Stamela, it will first pull all the images for all the packages, including CASA, various versions of CASA, WStream, DDFacet, Cubicle, and a whole host of visualization tools, flagging tools such as Andre Fringa's AO Flagger, R flagging tool, Tricolor, etc., etc. So there's many packages here. I'm going to show you just how to simulate, for instance. Let's say you want to simulate your UV coverage. The simulation itself is done through a wrapper script called SimMS, and that calls on CASA internally, which writes out an empty measurement set for you that has fields in direction that you can specify as directions here. As you can see, the Stamela recipe is a Python script, right? So it's a Python wrapper that calls, that will instantiate containers, and it will run the software packages inside those containers. So they execute all inside their own little bubble. So there's no interference between different packages, for instance, that you would get for a single virtual environment installing a lot of packages alongside each other. So here we're simulating an empty measurement set for Meerkat in some direction at declination 30. Our synthesis time is in hours here. Our integration time is 10 seconds. Center frequency is 750 megahertz. The delta frequency, so the step-in channel, is 1 megahertz here. And there's only one channel here. This can be set arbitrarily, of course. It will put the measurement set into what is called the MSDir. So there will be an input directory, an MSDir directory, and an output directory. We put it into the MSDir directory and write out any other outputs into the output directory. And that's in your current working path. And then you can, so we call this wrapper function, which is outside of CASA, the SMMS wrapper. And then, for instance, we can even execute basic CASA operations using this. So just a familiar list of the simulated measurement set. And you'll see that it now goes and executes the recipe. So you'll say Stamela run my script.py. You can call that anything. And it will say, okay, step 1, create my measurement set, which it gets from your label, creating MS. Right, so step 1 is creating MS. Cab is SimMS. It will execute this. As I said, it's a wrapper around CASA. It provides some additional functionality of offsetting tracks inside the measurement set, for instance. So it provides quite fine-grained control, actually. So it executes and it calls CASA internally. CASA writes out a measurement set per scan. And then, as I said, the second step after that completes, so it will say container has executed successfully, runtime was that. So this is just a wall time. And then it will say, okay, step 2, get MS properties. We're going to call CASA list ops, as we said. And we get a list ops for our simulated Meerkat measurement set. So this will contain UV coverages for the Meerkat. So this is just a toy example. This is showing you how to construct a recipe. You can do imaging, you can do calibration, you can construct a full pipeline with this. And this is the tool underneath the hood that we use to actually build pipelines, at least in our team. So yeah, so that's one way of doing it. Then I'm going to show you my pipeline, which is based on Stamela. There's also the Caracal pipeline, which is much more flexible than mine. Mine is really targeted towards doing cluster continuum imaging. Caracal is much more sophisticated. So if you want to not only image on Meerkat, you want to image on the VLA, for instance, you can also use Caracal. But I'm going to show you just my pipeline. So basically what I provide is transfer calibration, polarization calibration, and self calibration through direction dependent calibration even. So you can, for instance, provide a single short recipe with reasonably optimal parameters for Meerkat. This pipeline, I should say, is specifically for Meerkat L-band. I'm looking into adding UHF capacity, but for Meerkat L-band, I provide some good guesses for initial parameters, and you can see that you construct a recipe for doing phase self-calibration. So this step will go and image mask, image again, and do CASA gain calibration for phases solved at, say, 256-second intervals, for instance. So you can construct a full recipe like this. So it's a phase self-cal, direction, delay and phase self-cal, amplitude and phase self-cal, make a final image at a robust setting, subtract the model I get from that. So I can subtract the AGN components out, for instance, to look at the diffuse emissions. And now we image again, and we can image at a higher robust setting. If you want, you can apply tapering options as well. So this is just an example of just a recipe, and it's just shorthand. And internally, what it will go and do is say, let's look at direction-dependent calibration. At this point, you've made your image already, so there's some imaging steps here earlier on. Inside direction-dependent calibration, just to show you how we can invoke cubicle, you can also invoke this, of course, outside, in a virtual environment, just from the command line. But I'll just show you some example parameters for cubicle for doing direction-dependent calibration. first we're going to run, we do a tagging operation. So we draw these 9 regions semi-automatically. So I've written a little script to do some local noise estimations around sources that can be provided through, say, a DD facet residual image. It will construct, it will tag regions that may need direction-dependent calibration. You can open that up in DS9 and add further regions if you want. And then we take that regions file and we take the model, component model file you get from DD facet. So it's DICO model file, and you plug that into Cubicle. Now, Cubicle is just a calibration package, just like the CASA gain or bandpass calibration tools. So this is executed on our data set. We can ignore some of the parameters here. It's just chunking just to make things parallel, for instance. And the way we specify the model here to construct that exact rhyme that I showed you earlier is the model data is going to be the first direction that we solve for. So direction 0 is model data as it's output by the imager, say DD facet, but this can be another imager as well. Then what we're going to input here in this case is a component model from DD facet with our tagged regions, so that DS9 region file, right? So this is just substituting in, but you can think of this as just specifying a component dictionary at the regions file, both just paths, right? And we're going to subtract all of that from the model data. So that's just going to leave us with all of the flux that is not subject to any calibration errors. Then if you say colon, you're going to provide the next set of directions. So this will be direction 1 through N provided by, again, that same dictionary with the tag. So now it will just have just be the model stemming from all the different parts of the sky that have direction-dependent errors and that we want to solve for. So, excuse me. So now basically what we're going to say, you can, again, as in CASA, you can apply cutoffs in the baselines, etc. It's just different names here, but you can look at the help file. It's pretty explicit. Now we're going to solve for direction-dependent gains and for direction-independent gains in one go. The direction-dependent gains is going to be applied to all of our directions. So we're only fixing direction 0. So this will have only a direction-independent gain applied. So this model data minus all of the visibility stemming from the directions that are subject to errors is direction 0. So this whole thing here, the highlight, is direction 0. So that's we're going to fix. That's going to only have a gain solution applied. Remember that we have gains on the outside, so G in that equation, if you recall. And we're going to just do phase calibration on that, for instance. And we're going to do a direction-dependent calibration, so a amplitude and phase solution, complex 2x2 on the patches of sky that we want to remove, right? So we're going to apply, we're going to solve for gains, apply gains towards those directions, and we're going to say in my corrected visibilities, I want those patches of sky removed. They're not useful to me. They're adding interference. I want to peel them off. So just as we do peeling of CASA by removing those patches of sky, we can do peeling of any number of patches of sky simultaneously with Cubicle. So it just makes the whole process much, much easier. So this is how we peeled off, for instance, that little buggersome source over here using Cubicle. You can tag any number of regions using this approach and it will all be done simultaneously.